Hi, Hitashri. Good evening. Good evening. Can you hear me? So I'm visible and audible to you, right? Yes. Okay. So let's wait for one more minute and then start the class. Legal Warriors official. Such a good idea. Hi, Sumati, and hi, Devil Warriors official. Hi, Hitashri again. Good evening to all of you. Okay. Tejashwini. Yes, I think we can start the class. So good evening to all and all again, and myself Anandi, and we were discussing about the D and F block elements, right? And in the last class, we have completed the general properties of D block elements. So there were many general properties we have discussed. Especially in the last class, we have covered the formation of colored ions and alloy formation and something magnetic property and the formation of complex compounds. So those things we have discussed. All those are very important. Okay. Now, and also we have discussed the compounds. So there are two compounds I told you. One is potassium dichromate and the other one is potassium permanganate. So potassium dichromate was discussed fully, its preparation, its chemical properties and its color, oxidation state, the structure of the dichromate and chromate ions, everything was discussed. And I told you all the points under the compounds are very, very important. And moving on to the second compound, the potassium permanganate. So the preparations were discussed in the last class, preparations of potassium permanganate. And some of the reactions also I have discussed. So I'll continue with that. So coming to KMnO4. So we have discussed the oxidizing nature of the KMnO4. Right. So KMnO4 like K2Cr2O7 is also a powerful oxidizing agent which oxidizes many compounds. And also I told you in acidic medium, it can oxidize very well. That is, it can get, it will oxidize the other elements and they themselves will get reduced. So from +7 till +2. And in basic medium, there is the oxidizing power becomes very less. So it is moving from +7 till +6. And in neutral medium, some moderate oxidation is there. From +7 till +4. So it can gain 3 electrons. Okay, moderately. It is okay. So this is what we have seen in the last class. And also I told you sulfide is oxidized to sulfur, sulfur dioxide to sulfuric acid, arsenide to arsenate, sulfide to sulfate, nitrite to nitrate, ferrous sulfate to ferric sulfate. These are the conversions of the action of KMnO4. And also iodide to iodine, hydrogen peroxide to oxygen, oxalic acid to carbon dioxide. And this was the summary I gave you in the last class. So this was discussed in the previous class. All these reactions are done in the acidic medium. Okay, all the conversions which we have discussed so far, they are the acidic medium conversion. Now, coming to the basic medium and neutral medium for today's class. So, in basic medium and in neutral medium, iodide is getting converted to iodate. Iodide is getting converted to iodate. That is, the -1 state of I is getting converted to +5. So, how many electrons are lost by iodine? Can any of you tell me? Can anyone tell me how many electrons are lost by iodine? It is going from -1 till +5, right? So, -1 to 0, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 5, 4 to 5. So, totally 6 electrons are lost by iodide ion. Okay. And who has gained those 6 electrons? This KMnO4, manganese. It only oxidized this iodide. So, iodide is getting converted to iodate. So, you have to be very careful. In case of acidic medium, iodide is getting converted to iodine. Okay. But in case of basic medium, it is not the same case. Iodide is getting converted to iodate. So, this was the question asked in the last year JEE NEET exam. Okay. So, in alkaline or fairly basic medium, the iodate is, the KMnO4 oxidizes iodide to what? Okay. So, the answer is iodate. You have to be very careful. In acidic, I minus is getting converted to I2, but in basic, I minus is getting converted to iO3 minus. So, I minus to I2 in case of acidic medium, the same iodide to iO3 minus in case of basic medium or fairly basic or neutral medium. Clear? So, this was the question asked. And in JEE 2022, yes. So, all the questions related to D and F block elements lesson, as I already told you, I will discuss in the Saturday's class. Now, it can also oxidize manganese +2 state to manganese +4. Manganese sulfate is getting converted to manganese dioxide. Okay. And this is the manganese from potassium permanganate. This particular manganese is oxidizing a manganese salt. So, this manganese is different. Okay. This manganese is different from this one. This is the oxidizing agent and this is the compound which is getting oxidized. Oxidizing agents are the electron acceptors, right? Oxidizing agents are electron acceptors, and this KMnO4 is accepting 2 electrons from this manganese sulfate salt so that it is getting oxidized to +4. And coming to next one, sodium thiosulfate is moving on to sulfate, sodium sulfate. That is +2, oxidation state of sulfur is changing from +2 till +6. Means how many electrons are lost by sulfur? 4 electrons are lost by sulfur. Okay, so here how many electrons are lost by manganese salt? 2 electrons are lost. Clear? Fine. I'll go with the uses of potassium permanganate. So these are the reactions under acidic and basic medium which we have to go through it properly. Yeah. So coming to the uses of KMnO4. So the first uses, it is used in the volumetric titration estimation, which you might have did in your school labs. I hope you might have come across this part, volumetric analysis part in your lab, right? Am I right? If I'm wrong, sorry for that. So for the estimation of ferrous salt, oxalates or oxalic acid and hydrogen peroxide purpose, we are using KMnO4. So you can see the system, right? So this is called as burette. So in this burette only, we fill the solution. What solution we will fill? We will fill this potassium permanganate solution with, only, which is purple in color. Okay, this is a conical flask where we do the reaction. by adding drops of KMnO4. So KMnO4 is used in volumetric estimation, and it is used in the bleaching of wool, cotton, silk, and other textile fibers. You can see for bleaching purposes. So by doing the bleaching, the color of the cloth changes, no? Color of the fiber changes. So for bleaching purposes, they are using KMnO4. And for decolorization of oils, and the alkaline KMnO4. Alkaline in the sense some basic KMnO4, which is called as Bayer's reagent. Alkaline KMnO4 is called as Bayer's reagent. It is used as an oxidizing agent. You can see the role of alkaline KMnO4 in your class 11 hydrocarbons lesson. In hydrocarbons lesson, under the reactions of alkenes, you might have seen this. So alkenes will be oxidized to alcohols in presence of alkaline KMnO4. Okay? So it is an oxidizing agent. So the next is F block. So any doubts so far in the D block? Any doubts so far in the D block? From the properties, from the compounds preparation, uses, and the chemical properties of the compound, structural informations. Any doubts, students? If you don't have any doubt, put yes in the chat box. Or if you have any doubt, tell me the doubt. I'll clear you. I'll try to clear. Just tell something, na, whether you have understood or not. Okay, I'll go for F block elements. F block elements. So the first part of the lesson is over. That is D block, and the second is F block. So F block elements majorly consist of lanthanoids and actinoids. F block elements are called as lanthanoids and actinoids. So let's first discuss about the lanthanoids and then discuss about the actinoids. Okay. So coming to the lanthanoids and actinoids, I'll show you the position of lanthanoids. So we all would be knowing this. We know the S block, P block, D block, and all. So the F block you can see in the bottom part of the periodic table. So you can see there is an element called lanthanum, and from lanthanum onwards, it proceeds till lutetium. And the actinoid starts from actinium and ends with lawrentium. Okay, so these two rows consist of F block, and the first row, which you can see in the slide, is called as lanthanoids. Okay, the second is actinoids. So these are the lanthanoids and actinoids, and lanthanoids are called as 4F series and actinoids are called as 5F series. Now coming to the electronic configuration of lanthanoids, this is the energy levels which we will be using to fill up the electrons according to the energy level. So in case of praseodymium, which is a lanthanoid, the electronic configuration runs like this. So from 1s, 2s, 2p, then 3s, 3p, 4s, 3d, 4p, then 5s, 4p, 5p, 6s, and 4f. After 6s only, the 4f comes. Okay. So the last electron enters into the F orbital. So that's why it is called as F block elements. Okay. As you can see, the last electron enters into the F orbital. And the electronic configuration, general electronic configuration for all the lanthanides is 4f1 to 14, 5d 0 to 1, and 6s2. This is the general electronic configuration for lanthanoid, which is very, very important. Okay. So the minimum value of N should be 6 minus 2 will give you 4. Okay. This is for lanthanoids. And there are some exceptions for this configuration. Lanthanum, cerium, gadolinium, and lutetium. These 4 elements will not follow this particular electronic configuration order. Okay, which is 4 of 1 to 14, 5D 0 to 1, and 6s2. So let me show you the exception in the next slide with the tabular column. So you see the exception was given for lanthanum, cerium, gadolinium, and lutetium, right? So you see here, the configuration was 4 of 1 to 14, 5D 0 to 1, and 6s2. But you see here, in case of lanthanum, no F orbitals are present. And in case of cerium, you see, in 5D, you have 1 electron. And 4F has only 1 electron. This is an exception. And in case of gadolinium, from praseodymium till europium, you can see the order. It is 4f3, 6s2, 4f4, 6s2. Okay. So one of the F electron jumps into the 5D orbital for cerium. And in case of gadolinium, so after 4f7 here, it should be 4f8, right? So the 8th electron has jumped into the 5D orbital. And for lutetium, you see, so after 4f14, that should be 4f15. But 15 electrons cannot be accommodated in the F subshell. Since we have only 7 orbitals for 4f, only 14 electrons can be accommodated. So the next electron comes to the 5D. 15th electron comes to the 5D. So why there is an exception to these? So for gadolinium, there is an exception due to the formation of half-filled F orbital. Due to the formation of half-filled F orbital, which is stable, the 8th electron jumps into its nearest 5D energy level orbital. Okay. The same way here also. Due to the fully filled configuration of 4f subshell, the last electron enters into the nearby 5D orbital. Okay, to give these configuration. So there is an exception like we have seen in D block for chromium and copper. Here we are facing it for gadolinium and lutetium for the same half-filled and completely filled reason. Okay. Now coming to the next atomic and ionic size property, which is a physical property of lanthanoids. So there is a tabular column shown to you for all the lanthanoid elements. It is lanthanum, cerium till lutetium. So for the neutral lanthanoids, the radius are given in terms of picometer. And for lanthanide 3+ ions also, the ionic radius is given. So from lanthanum to lutetium, from left to right. So left to right across the period, the size decreases. That is a general trend for the whole periodic table, right? So from left to right, here the values are, here everything is given one after the other. So the arrow is from top to bottom, but in the periodic table, they are in a left to right manner, right? So from left to right, atomic size decreases and ionic size also decreases. But you can see the exception for europium. You can see the exception for europium. Okay, that is an exception. Just a second. For europium, there is a slight exception, difference in the size. Clear? You can see the graph to you, the size decreases. So for lanthanides, from left to right, atomic size and ionic size decreases. Clear? For lanthanide 3+ and lanthanide. Now coming to the oxidation state property of lanthanoids. So the most common oxidation state for all the lanthanoid elements is +3. Okay, the most stable is +3. And the least stable is +2 and +4. Least stable is +2 and +4. So for cerium, you would see the configuration is 4f1, 5d1, and 6s2. This is the configuration of cerium. And there are 4 electrons in the cerium. Valence electrons are 4. Okay. So what does it do? It loses all its 4 electrons and it becomes 4f0, 5d0, and 6s0. So cerium will exist in +4 state. Cerium will exist in +4 state. But since +3 is the most stable oxidation state for all the lanthanides, it gains 1 electron and it acts as an oxidizing agent by gaining 1 electron and it turns to +3. So the electron gaining system or the species are called as oxidizing agents, right? So they are oxidizing in nature and it turns to +3 from +4. Strong oxidizing agent. And praseodymium and neodymium and terbium and dysprosium. So all these 4 elements are the exceptions. All these 4 elements are existing in +4 oxidation state. All these 4 exist in the +4 oxidation state. You have to note the exceptions, okay? It is very important. So cerium exists in +4, but it turns to +3, acting as an oxidizing agent, and these 4 elements are exceptions. In their oxide form, the oxidation state is +4 for them. Clear? Now coming to europium. Europium configuration is 4f7 and 6s2. So 4f7 is half-fill configuration, which is more stable. So europium will not give electron from its 4f subshell. So only the 2 electrons which is present in 6s orbital will be removed. So it exists only in +2 oxidation state. But since +3 is the most stable, it loses out its electron. One of the electron from europium is getting lost. One of the electron from europium is getting lost, and it is turning to +3. Okay. So the electron donors are called as strong reducing agent. They are called as strong reducing agent. And coming to ytterbium, which is 4f14 and 6s2, again fully filled is more stable, from which we cannot remove the electron. So only the 6s electrons are removed, and europium also exists in +2 oxidation state, which is again a strong reducing agent. Clear? Terbium. Coming to terbium. Terbium +4 is the most oxidation state, and it gains an electron and acts as strong oxidizing agent. Same is the case with samarium also. Samarium exists in +2 and it loses one of its electron and turns to +3 by acting as reducing agent. And these are the oxidizing property of and the reducing property of all the lanthanoids. Clear? Any doubt? Any doubt you have? So you have to read the compounds which are stable in +4 oxidation state, and you have to read the compounds which are stable in +2 oxidation state. And +3 is the most common. All the elements will try to exist in +3 by donating or accepting the electrons. Students, is that clear? Fine, I'll go for physical characteristics of lanthanoids. Lanthanoids are silvery white soft metal. Lanthanoids are silvery white soft metal. You can see the cerium and dysprosium on your screen. Silvery in color, just white. Okay, soft metals. And they get tarnished rapidly in air. Tarnishing in the sense they get oxidized so easily by the oxygen which is present there in air. And the hardness increases with atomic number. Across the period, the hardness of the element increases. Means the lanthanum, cerium, they'll be a soft in nature, and ytterbium, lutetium, they are very hard. So the hardness increases across the period. Clear? And the fourth property is they are the good conductors of heat and electricity like D block elements. Like D block elements, F block elements are also, basically lanthanoids are also the good conductors of heat and electricity. You see here, there is a lanthanoid element present here. It is conducting the electricity. It is conducting the electricity. So electron flows in this direction, so means the current will be in the opposite direction, right? So they carry the current as well as the heat. And the lanthanoids ions show color in both solid state as well as in aqueous solution. D block metal ions, they show color only in aqueous solution, but here lanthanide ions, they show color in both solid state as well as in aqueous form. And they are paramagnetic accepted to this. Okay. Lanthanum 3 plus, cerium 4 plus, ytterbium 2 plus, and lutetium 3 plus. So why there is an exception here? So let me come to the lanthanum. Lanthanum will have 3 electrons, and by removing those 3 electrons, you will have 4f0. And cerium also contains 4 electrons, right? Just now we have seen like 5d1 and 4f1 and 6s2 for cerium, right? So all the 4 electrons are removed. Now 4f has 0 electron. So since there are no unpaired electrons present in it, it is they are diamagnetic in nature. These 4 ions are the exceptions to this paramagnetism. And in the ytterbium 2 plus, if you see, it will contain 4f14 fully filled. And lutetium 3 plus also 4f14 fully filled. So these 4 ions are the exceptions. Other than these 4 ions, all other ions formed by the lanthanides are paramagnetic in nature. So these 4 ions are very, very important. They may ask you to find out the ions which are diamagnetic in nature by giving 2 ions in the options. Okay, you have to read these 4 ions. So these are some of the physical characteristics. First is about the physical nature. Next is the oxidizing property and hardness, conductivity property, and the formation of colored ions, and here magnetic property. Okay, so all the physical properties of lanthanides are here. And the next property is melting point and density. It increases with atomic number because once atomic number increases, the mass of the substance increases. So what is density? Density is equal to mass by volume. If the mass increases, density also increases. So that's why density increases. And if the mass is very high, then that particular substance will get melted very late only. It will take some time to get melted. So melting point also increases as the mass increases with atomic number. Clear? Clear for all? As the atomic number increases, mass of the substance increases, and mass and melting point, they are directly proportional. So melting point also increases with density. So this is the order, directly proportional order. For europium and ytterbium, again half filled and fully filled configuration, they are having very high melting point. Okay, they will not melt so easily since they are very stable. Now coming to the chemical properties or the chemical characteristics of lanthanides. Lanthanides forms, they react with hydrogen, oxygen, nitrogen, carbon, water, or you can heat it, decomposition occurs. So all such reactions are possible with lanthanides. So lanthanides, they are represented by the letter Ln. And if a lanthanide is treated with acid like HCl or hydrochloric acid, H2SO4, if it's treated with an acid, it evolves hydrogen. Okay. And if a lanthanide is reacting with halogens in the sense X2, fluorine, chlorine, bromine, iodine, it forms halides of type LnX3. If your halogen is chlorine, then what will be the formula? We will have LnCl3, right? So it forms halides with a +3 oxidation state since it is the most stable form. And if it reacts with water, lanthanides with water forms hydroxides. It forms hydroxides with +3 oxidation state. For each OH, 1 minus is the charge, no? They form hydroxides. So with acid, hydrogen gas is evolved, and with halogens, they are forming halides, and with the water, they are forming hydroxides with the evolution of hydrogen. And if it is treated with carbon, they are forming carbides. You have to note the formula. It is LnC2. Carbon exists in LnC2 form only. It is heated with carbon at 2773 Kelvin to form carbides to form carbides. And it is treated with nitrogen to form nitride of formula LNN, nitrides, because the charge of nitrogen is -3, right? So it is +3. So only one nitrogen has to be given. Okay. And when it reacts with sulfur, it forms sulfides. Sulfur is oxygen group member, right? So the charge will be -2 for one sulfur, and for 3 sulfur it is -6. So -6 charge is given to two lanthanides. -6 charge is given to 2 lanthanides. So one lanthanide will get +3. Okay. So the oxidation state of lanthanide is +3. So it forms sulfides. And when it is treated with oxygen, it forms oxides. So again, oxygen, no. So charge is -2. 3 into -2, -6. -6 is shared by 2 lanthanide. So one lanthanide charge is +3. Clear? So these are the chemical reactions of lanthanides. Any doubt? Any doubt in the chemical reactions? No doubt. Shall I move with the actinides? Thank you, Sri Harshini, for your response from class 12. Thank you. And coming to actinoids, so you have to note all the points from lanthanides, that is electronic configuration, all the general properties, physical properties, and there were some exceptions also, right, in paramagnetism and in oxidation state, +3 is more stable. So all the things are very important, including the chemical properties, which we have discussed in the last lecture. Now coming to actinoids, actinoids are also an F block element, 5F series. Actinoids belongs to 5F series. The last electron enters into the 5F orbital. Okay, from actinium till lawrencium it has. And actinium, thorium, protactinium, they exist in the nature. These 3 elements exist in the atmosphere. Okay, the remaining elements from uranium till lawrencium, they are man-made elements. They are man-made elements. Okay, so which can be obtained from artificial process in the laboratory or in some places from man. Okay, man-made elements. So first 3 are the elements present in the atmosphere. Got it? So most of the major elements of actinoids are man-made elements only. Here from uranium till lawrencium. This is very important. From uranium till lawrencium. Okay. Coming to electronic configuration of actinoids, you can see again for plutonium, an example is given for plutonium. Last electron enters into 5F orbital for actinoids, and the electronic configuration is 5F1 to 14, 6d0 to 1, and 7s2. And here the n value is 7. n-1 is 6, and n-1 is 6, and n-2 will be 5F. Okay. Exceptions: actinium, thorium, protactinium, uranium, neptunium, curium, and lawrencium. These are the exceptions to this given electronic configuration. Okay. You can see here the tabular column for actinoids. As I have told you, the exceptions are observed in actinium, thorium, protactinium, uranium, neptunium, curium, and lawrencium. Okay, the electron spinning, you can see electrons are mostly added into the 6d orbital. You can see in these cases, electrons are added to the 6d orbital instead of getting added into the 5f orbital. Why? So for curium and lawrencium, we know the reason, that it is due to the stability of half-filled configuration for curium and fully filled configuration for lawrencium. The electron is jumping into the 6d orbital. For these elements, the electrons are jumping into the 6d orbital because the energy levels, the 5f 6d, and 7s. Those energy levels are very near. They are of very comparable energy. They are of very comparable energy level. They are very closer to each other. All the energy, 3 energy levels are very closer to each other. So the electron which has to come to 5f orbital, actually they enter into the 6d. Since the energy difference is very small between 5d, between 6d and 5d. Okay. And coming to the atomic and ionic size, the radius, as I've told you, across the period, size decreases, right? So here I have given you in the opposite manner. It is increasing from right to left, or it is decreasing from left to right. Last electron, you see, it is in the 7th shell. The shell number 1, shell number 2, 3, 4, 5, 6, 7. So in 7s, we put 2 electrons, right? So these 2 are those 2 electrons. Okay. 7 is 2. Now the distance between 7 is this 6d and 5f. So the energy difference between these orbitals, they are very small. That's why the electron jumps here and there. Okay. Now coming to the size with values. So it is given in terms of picometer again. You can see the size for M3 plus and M4 plus ion. It decreases from left to right. That is from actinium till lawrencium. Ionic size also the same thing. Coming to oxidation state, +3 is the common oxidation state for actinoids. +3 is the common oxidation state for actinoids, and +4, +5, +6 and +7 also exist for some elements. For which element they exist? For the early inner transition elements. For the early inner transition or F block elements. Since F blocks are under the D block, it is called as inner transition elements. D block is called as transition elements. No, since we are getting the F block from D block, it is inner transition elements. The early inner transition elements are exhibiting or they are having variable oxidation states, but the post 5f elements, the post inner transition elements, or especially we can put 5f, post 5f series, they do not exhibit multiple oxidation state. Okay. So 5f series, they basically exhibit variable oxidation state. Why do they exhibit variable oxidation state? Due to the comparable energy level of 5f, 5f, 6d and 7s orbital. Okay. They are of comparable energy levels. Comparable energy levels. So this is the reason for the variable oxidation state of early inner transition elements. Okay. So they can go in and come out electrons, they can gain electron. Mostly they give their electron and they exhibit in +4, +5, +6, +7 state. Okay. Coming to the physical characteristics of actinoids, it is silvery in color again. Neptunium, you can see, and they are highly reactive, especially in finely divided form. So thorium, they have divided the thorium into powder. So in powder form, thorium is highly reactive. Okay. They are paramagnetic in nature, means they contain unpaired electron in it mostly, and they get oxidized in air. They get tarnished in air due to the formation of oxide coating. Okay. Suppose if this is our neptunium metal, so the oxygen will come and react with it and form the oxide layer here so that it gets tarnished. The other elements cannot come and react with this particular element. Okay. And the difference between lanthanoids and actinoids is shown to you. Just take a screenshot of it. So this is your oxidation state. +3 is the most common state for lanthanoid. And here also +3 is the most common, but some other is also possible because of comparable energy level. And binding energies of 4f are higher, 5f are lower. 4f electrons have greater shielding effect. This point is very important. 4f electrons have greater shielding effect and the 5f electrons have poor shielding effect. So the tendency to form complex is very less. So comparatively, they have high tendency to form the complexes. Lanthanoids are less basic. Actinoids are more basic. Promethium is the only element which is radioactive. All actinoids are radioactive. And here everything follows, no, not everything, most of the ions follows colorless ions, and some of the ions of actinoids are colored. Uranium 3+ is red in color, 4 is green in color, uranium 2+ is again yellow in color. So some of the ions, uranium ions, are colored. And coming to magnetic property, mostly they are paramagnetic, and I have told you 4 exceptions. No, those are diamagnetic, and they can be identified. Here also they are paramagnetic, but it is very difficult. To explain the magnetic properties of actinoids. And they do not form oxoanions. Actinoids, they do not form oxoanions. Lanthanoids do not form oxoanions, but actinoids form oxoanions, which you can see here in the slide. Okay, oxocations. So this is the difference between lanthanoids and actinoids. So here, take this third point as very important point, and oxidation state is also very important. And radioactivity, the only element which is radioactive in lanthanide is promethium. And here I have given you some exceptions for paramagnetic character in the slide. That is important. These are very important. All are important. These are very important points. Okay. Clear? Shall I move on to the next slide? Thank you, Sri Harshini. So the next topic is applications of D and F block. So what are the applications of the elements which we have studied here in this lesson? This is the last topic of this lesson, applications. The first application is iron and steel are used in the construction purpose, as we all know, right? Iron and steel, they are used in the construction purpose. And tungsten is used in electric bulb. What is the formula for tungsten? W, right? In all the electric bulbs, you can see the tungsten filament. So why tungsten is used in the electric bulb, which is a D block element, is used in the tungsten filament? Because the melting point of tungsten is very high. Melting point of, very good. Melting point of tungsten is very high. Good. That's why it is used in the filaments, tungsten filaments, to withhold the temperature. Okay. And titanium metal, again a D block metal, is used in aircraft. Okay, for making the plates. Okay. And titanium dioxide is used in pigment industry for making pigments, since they are able to produce a color. They are forming this pigment industry for making colors. And manganese dioxide is used in the tri-battery cell. You might have studied this in your electrochemistry lesson. So here we use a paste, right? Paste of manganese dioxide. So there are D block element manganese being used. And copper, silver, gold, they are coinage metals, which were being used for making coins. Okay, copper, silver, gold coin, copper coin, silver coins we are having, no? They are coinage metals, which you can see here. First one is silver, second is copper, and third is gold. Okay. And vanadium pentoxide is used as a catalyst for the manufacture of sulfuric acid. This we have discussed in the class also. So vanadium is the D block metal which is being used. Okay. So how many users? There are 7 users in this slide, and some more users are also there. Iron is used as a catalyst in Haber's process. This also we have discussed. And AGBR, silver bromide, is used in the photographic industry for making the films, no? So it is having the photographic, it is used in the photographic industry, AGBR. It's used as a solution. Okay, AGBR solution only, they'll dip the films and they will wash. In olden days and all, they used to wash the photos, no? In a solution. In that solution, AGBR is used where our silver is the D block metal over there. So that's all. So that's all for D and F block. Okay, we are done with D and F block. So the lesson gets over here. So what you have to do, you have to go and study this lesson once again, and you have to solve more number of questions in it. Okay. So all the properties from today's class under lanthanoids and actinoids, you go and study. Okay. On the preparations were not discussed, sorry. The properties, chemical properties and physical properties, oxidation states of both, and the difference between the tabular column I gave you, know, that is very important. Take a note of it. And at last, uses of D block and F block, they are again very important. And the compounds which I told you, that KMnO4 compound and K2Cr2O7 compound. So again, an important topic of this lesson. And before that, we had the general properties of D block. So from general properties, we cannot mention that this is important, that is important, because all the properties are very, very important. Okay. So study the lesson, students. And tomorrow, I'll start with a new chapter. Okay. I'll go with a new chapter. Maybe I'll start with coordination compounds. Again, a very important and weighted chapter for both JEE Mains and the NEET. So tomorrow, let's start with coordination compounds, and on Saturday's class, I will discuss all the previous year's questions and some more questions related to D and F block elements. Okay. So if you have any doubt, you can ask me. Otherwise, we can meet in the next class. If you have any doubt, you can put it in the chat box. No doubt for anyone? Okay then. Thank you so much for listening the lecture. See you all tomorrow. Thank you. Thank you, Sri Harshini. Thank you so much. Thank you for all.